Today's Maths for Real is all about your favourite Greek mathematician and mine, Pythagoras, and his world-famous theorem. Now, it's all to do with calculating the length of the sides of a right-angled triangle, and I'm hoping that the army have put this theorem to good use right now, because if they haven't, I'm going to end up a couple of feet shorter than I already am.
This is a right-angled triangle, and it's called that because this angle here is exactly 90 degrees. Another feature of a right-angled triangle is that one side is always longer than the other two. This longest side is known as the hypotenuse, and it's easy to spot because it's always opposite the 90-degree angle. Now, what Pythagoras discovered was that the sides of a right-angled triangle have a special relationship to one another. First, draw a square on each side of the triangle. The special relationship is that the area of the square on the hypotenuse, this square here, is equal to the areas of the squares on the other two sides added together. Confused? Well, watch this. As you can see, the area of the two squares on the smaller sides exactly fits the area of the square on the hypotenuse. If we call the sides A, B and C like this, we can convert what you've just seen into a useful formula. The area of this square will be A times A, which is the same as A squared. The area of this square is B times B, which is B squared. And this area is C squared. So the area C squared must equal A squared plus B squared.
Here's a different triangle, but it's still got a right angle, so we should be able to prove that C squared equals A squared plus B squared. Cut out this black area of the square on C, and it will fit snugly into the area of the square on A. And the rest of the pieces will fit exactly into the area of the square on B. And that's Pythagoras' theorem. Pythagoras stated that the area of the square on the longest side of a right-angled triangle is equal to the sum of the areas of the squares on the other two sides. Now where, you might ask, would you want to measure a hypotenuse outside of your maths lesson? Well, remember the aerial ropeway that I was messing around on earlier? It started off its life like this. Here at the Army training camp in Strensall, we have a tower that is 15 metres high, and we have an anchorage point that's 25 metres away. Now, the Army know the anchorage point needs to be here in order for the rope angle to be safe. Any closer, and the angle would be too steep, and any further away, and, well, you're going to be running out of field. Now, if you look at it from the side, you can see that the tower and the ground actually form a right angle. That sings just a little bit like that. Now then, if we add in the rope from here to here, what we've got is a right angle triangle, the rope being the hypotenuse. Now what the Army needs to know is how long that piece of rope has to be, which is actually going to be quite difficult to measure, but not if we use Pythagoras' theorem.
Remember, C squared equals A squared plus B squared.
Is the hypotenuse, so we're going to label that C. The height of the tower is A. The distance from the tower to the anchor point shall, from this point forward, be known as B. Now, we already know that the height of the tower is 15 metres, and we also know that the anchor point to the tower is a distance of 25 metres. But we don't know what C is.
Using our formula, C squared equals 15 squared plus 25 squared, which equals 225 plus 625, and that equals 850. But how do we find C? Well, you've got until the guys sort out the rope slide to work it out.
what we do know is that c squared equals 850. Bang. Now, what we need to work out, though, is what c is. So, to work out what c is, we need to do the opposite of squaring, which is called taking the square root, which is drawn like that. So, c equals the square root of 850. Now, the square root is this button here, and all you have to do is whack in 850 on your calculator, press the square root button, and we see that c equals 29.15475947 metres. Now, obviously, we can't measure a rope to that sort of accuracy. It would be impossible.
So I'm going to round it up to the nearest 10, which is 30 metres. For any right-angled triangle, if we know the length of the two shorter sides, we can calculate the length of the hypotenuse.
Pythagoras lived 2,500 years ago, and although he seems to have taken all the credit for his formula, there is evidence that the Chinese, the Babylonians and the Egyptians had the same idea thousands of years earlier. Take the Egyptians and the construction of the pyramids. Each pyramid has a square base, but how did they get such perfect right angles at each corner? Well, the story goes that they used knotted ropes like this one. In fact, ancient Egyptian surveyors were known as rope stretchers. Now there was I, hoping that the Maths for Real budget might just stretch to a trip to Egypt, but no. Here I am at Bradford City Football Ground. Now, between us, me and the youth team are going to be checking out the corners of their pitch. Are they really perfect right angles? Here's the trick. The Egyptians knew the magic of what's called the 3-4-5 triangle. What they do is get some rope and tie it into 12 equal lengths and then make a triangle. They'd put 3 lengths down one side, 4 lengths down another, and 5 down the final side. And here they'd have a perfect right angle. And we know that this is a perfect right angle triangle because it obeys Pythagoras' theorem. Check out the maths. If it's a right-angled triangle, then a squared plus b squared should equal c squared. So let's see if this is true. A is 3, b is 4, and c is 5. 3 squared is 9, 4 squared is 16, and that's 25. 5 squared is also 25, so there you have it. A squared plus b squared equals c squared. If the sides of a triangle are 3, 4 and 5, the only kind of triangle it can be is right-angled. A 6, 8, 10 triangle has a right angle as well. It also works with a 5, 12, 13 triangle. A group of 3 whole numbers that obey the theorem are known as a Pythagorean triple, and ancient mathematicians were always keen to find other whole number triples. Maths exams often feature them, so it's worth remembering that a 3-4-5 triangle and a 5-12-13 triangle both have right angles. See if you can find some other whole number triples.
OK, this is the bit where Katie and I both tackle a question, but only one of us does it correctly. The other makes a deliberate mistake, and you've got to spot who makes it. You decide, do you tick it or trash it?
This week's problem is about a man stranded at sea. He is stranded 90 metres from the base of a cliff. The cliff is 50 metres high, and at the top of the cliff is a woman with a length of rope. The question is, how long does the rope have to be to reach the man? Pens at the ready?
Got it.
Go.
A man is stranded at sea. He's 90 metres from the base of a cliff. The cliff is 50 metres high, and standing on top of the cliff is a woman with a length of rope. The question is, how long does the rope have to be to reach the man?
The key to answering this is to realise that the man, the cliff and the rope all form a right-angled triangle. The hypotenuse is the length of the rope, so I've labelled that C. I've called the distance from the man to the cliff A, and the height of the cliff B. Now, from Pythagoras' theorem, c squared equals a squared plus b squared, which is equal to 90 squared plus 50 squared, and that's 8,100 plus 2,500. So c squared equals 10,600. The rope needs to be at least 10,600 metres long.
I also drew a triangle, but I called the distance of the man from the cliff B, and I called the height of the cliff A. Using c squared equals a squared plus b squared, c squared equals 50 squared plus 90 squared, which works out as 10,600. Now, to find c, I took the square root of 10,600, which is 102.95. To the nearest whole number, that's 103 metres.
So, who's right and who's wrong?
Is Ben right with an answer of 10,600 metres?
Or is Katie right with 103 metres?
OK, I'll own up, I made the mistake. I missed out the final step and didn't take the square root of 10,600. It's obvious, really. 10,600 metres of rope is a long bit of rope. To find c, you need to add a squared and b squared together and then find the square root.
Huge, graceful wind turbines like this one are popping up all over the countryside at the moment. They're an environmentally friendly way of generating electricity.
To choose a wind farm site, you first need to measure the wind speed, and to do that, you need to put up a temporary wind speed meter. It sits at the top of a tall mast like this, which is held up by metal guy ropes.
Which is exactly what Border Wind are doing here in Kirkheaton in Northumberland. Now, the mast is 9 metres long, and each of these outer steel guide ropes that you can just see are 10 metres long and are fixed into the ground by an anchor point, just like this one. The question is, how did the engineers know where to place the anchor point in order that all the outer steel guide ropes remain taut? Well, if you can see through all the snow, you'll notice that the guy ropes, the mast and the ground all form a right-angled triangle. Now, we know the guy rope is the longest side, so that's going to be the hypotenuse, so we'll label that C. The height of the mast we'll call A. And the length from the mast to the anchor point we'll label B. Now, we know that the guy rope is 10 metres long, so we can put that in. We know that the mast is 9 metres long, so that can go in as well. However, this time we don't know what B is. Now, the thing with Pythagoras' theorem is that as long as you know the length of two sides of a right-angled triangle, you can always work out the length of the third.
Remember, a squared plus b squared equals c squared. This time we need to work out b. Rearrange the equation by subtracting a squared from each side, and you end up with b squared equals c squared minus a squared.
So in this case, b squared equals 10 squared minus 9 squared, which is equal to 100 minus 81, which means that b squared equals 19.
Using this information, how far away do the engineers need to fix the guy rope from the base of the mast?